shikimic acid, which, like we talked about, was used to make Tamiflu for Naya and Beth. So this was this was the first reaction. All right, so sorry, there's like a car outside, I don't know if you hear it. Just as like a precursor, shikimic acid is an important biochemical metabolite found in plants and microorganisms, and one of its functions is to serve for the biosynthesis of aromatic acids. So in this first synthesis, we start with the Diels-Alder reaction here that forms to make these two bonds here. And then the next step is using osmonium tetroxide, which is just a syn dihydroxylation. So it's adding these two hydroxyl groups on either side of the initial alkene, and they're adding them in the same face. That's what the syn is indicating. And then here we have acetone that's used as a nucleophile for either of these hydroxyl groups, and it's going to basically just do an acetal reaction to put this group on the edge. So where the carbonyl initially was in the acetone is here, and then these are the two methyls of the acetone that was added.
The next step, can you go to the next slide, Emily?
Mm-hmm.
The next step is an elimination reaction when this OAC group is basically like pushed off and this double bond forms. MgO works as a base, which is like kind of weird because Scott said he's never really seen that before. And then it deprotonates this alpha hydrogen right here, and then the electrons from the alpha hydrogen go to form that double bond, and then the OAC is popped off. And this is like so easily done because the alpha hydrogen is very acidic.
Yeah, that's a very weird use of MgO. And it's also like, I think Beth was screwed up by like the magnesium bromide earlier. MgO is a little bit different in the sense that it's not that weird for sometimes for people to use metal oxides. It's a little weird to use metal oxides as bases, but not totally unprecedented. And then they had to heat it to like 300 degrees, which is also like a little also just, it seems like they probably could have found a better way instead of heating it with minerals to anyway, go ahead. Okay.
Next. Yeah. Okay, so this is just the removal or like the deprotectant of the acetal group. So it's usually done in acid and water, and it just kind of like takes it off. Yeah. The methyl ester is hydrolyzed to an alcohol, and the acetal pops off. Next. Okay, so this one is kind of like Beth's in that there are 3 steps in one, and they kind of just crammed it into one step. The first step puts the acetal group to protect all alcohols, so it puts an acetal here and here.
Esters.
Puts esters, sorry. Esters to protect the alcohol groups. And the second is when they add quinine. Quinine is protonated by the carboxylic acid, and it forms a salt. And this is important because it actually forms 2 enantiomers. So adding the quinine allows them to crystallize one form of the enantiomer and kind of remove whichever one they want to crystallize. And then they're left with the shikimic acid. And then the last step is just removing the esters with base. And then it leads to shikimic acid, which has a 15% overall yield, which is actually pretty good considering like it's like for an overall yield from start to finish. Yeah.
Okay, and then the next synthesis I had was a little more in depth, but it started the same way with the Diels-Alder reaction, just again to form these 2 bonds, and then the osmonium tetroxide to do syn dihydroxylation. But now here, this step is different. So this is called Peterson olefination. And in this case, it's used in acid, but a lot of times it's done like in the presence of bases, but here you're taking a beta hydroxysilane and it's going to decompose to form an olefin, which is just an alkene, and a silanol, which is a compound that has an SiOH attachment. So, and that's the one that's not seen here. So we're kind of just like getting rid of the silanol. It's not really important. So the mechanism for it kind of looks like this. So the PTSOH is going to be used to protonate this OH group so it can be ready to leave as water. And then this is how I interpreted how it gets pushed off as water. So a benzene here binds to the silicon, and then those electrons that bind it to the ring push here to make a double bond, and this leaves as water. So you're left with this double bond here. And then
So probably, Emily, that the pusher outer, the attacker of the silicon, is probably water.
that would make more sense.
Yeah, because that's how you would get the silanol product at the end, or which would be the trimethyl. You know what I mean? The trimethyl silicon with an OH group.
That makes more sense now that.
Yeah. So there must have been like a little bit of water in there too.
Oh yeah, that comes. Oh yeah, because you said that comes when you buy PTSOH. There it comes like in water. So when you're using it.
Yeah, it has like 1 water of crystallization. Like maybe just from looking at chemical ingredients every once in a while, you might have seen like if you look at a bottle of like copper sulfate, it's like CuSO4 and then .7 H2Os.
Mm-hmm.
That means when they crystallize it and then put it in the bottle to sell it, there's 7 waters in the crystal unit per unit of the actual compound. And that's true of toluene sulfonic acid, that it's always, I've never seen it otherwise. It's always toluene sulfonic acid H2O. So there is water in there. Mm-hmm.
So the water would be used to bind to the silicon. Silicon would make the double bond with its electrons here, and then more water would leave to form this double bond. So now the next, Lindsay, this is all you.
Yeah, so the next step is just forming an epoxide with MCPBA, which we learned about in Orgo 1. And then the next step is like kind of funky. It's when you form the bridge. And so what happens is the base, LiOH deprotonates the carboxylic acid in the Me, and and then the oxygen anion of the carboxylic acid attacks this carbon. I can't point. It's the carbon, the bottom, it's directly across from the OAC group. Yeah, that one right there. And then this causes the epoxide to open. And then the bridge is formed between the double bonded oxygen and the other oxygen of the CO2 Me. And then they add the acyl groups to protect the oxygens, the alcohol groups. Yeah. Sorry, it's a little hard without being able to point to see if you know what I'm talking about.
Yeah.
Does anybody have any questions on that?
That's a weird one too, because actually, I mean, in all of these, there's been a lot of like groups that are leaning over to open 3-membered rings, right?
Yeah.
So this one, it's actually reaching over from 2 atoms away, right? To open that epoxide, which is, I wouldn't predict that would have a chance of working. But it did, yeah.
So I think what's hard to understand between this, in this like blue star reaction here, is what becomes what, because like everything kind of changes, and they also rotate it, which doesn't help. So what's happening is this OAC group is going to leave. This carbonyl is going to become CO2 Me, and this O becomes the OAC. So here, this is where a double bond is forming. So it's kind of, Naya and Beth, it's kind of like your reaction, how it's just a lot combined to one. So that's what happened here. So this HCl-Me, that's transesterification reaction, and the OAC is right here is going to be acetylated by the acetic anhydride in the presence of pyridine. And then the DBU here is just a really strong base. It's got a really long name that I would murder, so I'm not even going to try. But it's a really strong amine base, and it kind of mimics the SN2 elimination from the first synthesis. So it looks something like this, where it's this hydrogen here is going to be stolen by the, no.
No, it's the one. It's the one, you can't see my pointer, but it's the one at the base of the ester, because that is the alpha hydrogen. So this is, remember, like the magnesium oxide in the 300 degrees baking that they did?
Mm-hmm.
It's the same as, it's the same as that. Now they're just using a more modern way and not an oven. But
this
the
makes
hydrogen,
sense because there's nothing there. Okay.
yeah, so it's always the hydrogen that's adjacent to the group that's leaving, and then its electrons flow down to make the alkene, and then the leaving group leaves.
Mm-hmm. So the hydrogen that's wedged here is the one that would be
Yes.
stolen, and those electrons would make the bond here, and that would
Correct.
push the OAC out.
Correct.
So that's how, like, that double bond forms there.
Yes.
And again, this has like a 29% yield, which is pretty, like, not bad for a whole overall yield. And each of these individual steps had pretty high yields themselves.
Yeah, it's pretty good, I think. Yeah.
Yeah, so does anyone have questions on any of those steps?
In the end, I noticed in your first synthesis it was minus, but in this one it has like plus minus. Does that mean it's racemic and they didn't select for a single enantiomer? I've never seen plus minus in like before.
I didn't even catch on to that.
I would say yes, that it's probably right.
Yeah, that's what I'm thinking.
Because like in the first synthesis, you know how we had to remove one enantiomer? I'm guessing we just didn't remove one of the enantiomers in this synthesis.
Yeah. And can you, Emily, but that is true, that plus minus implies that it's racemic. And Emily, would you mind going up to the first synthesis? Okay, I want to, yeah, so if you, okay, it looks to me like if they wanted to, they could do a similar step to here to purify the one enantiomer, the minus enantiomer. Because in the second one, if you go back down, they actually didn't make shikimic acid yet. They made, it's like the methyl ester of the carboxylate, and all of the alcohols are still protected. So first of all, it's kind of mislabeled because they're not actually quite done yet. They could make this into racemic shikimic acid by just adding like hydroxide and hydrolyzing all of the esters like all at once. Or they could sort of go through it and make the sort of acid and then make the salt with whatever they used, quinine or whatever, and then separate the enantiomers and then hydrolyze the esters. But they didn't show that, I guess. But they're not quite there. I guess they're not quite done yet. So it's a bit of a mislabel.
They also had a mistake in both of these syntheses. So if we look, just like look at this and remember what that looks like, it minus the deprotected, like these aren't protected anymore, these are OHs. If we look at this, the alkene here, this is like kind of dashed backwards. It's not really present in the correct like plane that it should be for an alkene, which was kind of misleading. And it was seen in both of these reactions.
Yeah. It's correct on the previous structure. Like that should just not be a wedge or a dash, like right there. It should just be a flat line. Yeah, that's the kind of stuff that should make you cringe a little bit when you see it, right? Because you're like, well, it's not a wedge or a dash at that position. So that's probably just like a chem draw error on somebody's part. And somebody else found a little error where they never made it was like a degree symbol, but they didn't make it into a superscript.
Yeah. It was just like OC, like multiple times throughout the reaction.
Yeah, and you were like, is it like cobalt that they misspelled or something? And it's like, no. They just never put the degree symbol up as a superscript. So these things happen. This one is kind of bad, I think, the dash on the alkene, because they did it in both of them. So hopefully somebody got yelled at some point for that. But
Yeah.
Nice. Any other questions? Do you like doing the syntheses and like